you can. Okay. Okay, hi everyone. Welcome to attend our Optical Photonic Computing System Seminar Series. This is our 7th seminar, and our seminar will be 1 hour, including 45 minutes presentation and 10 or 15 minutes Q&A towards the end. So if you haven't registered our mail list, please scan the QR code below so you can receive our email for the latest events. So also feel free to join our Slack channel for networking, and we also have a YouTube channel. So we use that to post any past events, video recording. So please share it with your friends, with other researchers to review the past seminars if they cannot join online. There are some logistics. So this event is already recorded. And if the presenter agrees later, we'll also share the videos on YouTube and also the PDF slides. So if you have any question, please, you can unmute yourself during the talk to ask any quick questions, or you can just type it in the chat box. Zhengqi will handle the Q&A towards the end. Okay, let me quickly give an introduction to the speaker. So very glad we invited Professor Nathan Youngblood to give a talk on photonic architectures for in-memory computing using non-volatile optical materials. So Professor Nathan Youngblood joined the Department of Electrical and Computer Engineering at the University of Pittsburgh as an assistant professor in September 2019. As a postdoc researcher at the University of Oxford from 2017 to 2019, he developed the phase-change optical systems and photonic architectures for non-volumetric computing. In 2016, he received a PhD in electrical engineering from the University of Minnesota, where his research focused on integrating 2D materials with silicon photonics for optoelectronic applications. Nathan leads the Youngblood Photonic Labs at Pitt, whose goal is to develop reconfigurable photonic materials, devices, and architectures which have potential to transform the fields of artificial intelligence by minimizing computing latency and energy consumption. Nathan's work has been published in leading journals such as Nature, Nature Photonics, Science Advances, and features in popular news outlets such as the Times, Lunton, and the Daily Mail. Okay, now the floor is yours, Nathan. You can try to share the screen.
Okay.
Stop sharing.
Can you see that okay?
Yep.
Great. Well, thank you very much for the invitation. It's a pleasure to be giving a talk at this seminar, and thank you very much for the organizers for inviting me. So kind of the main focus of my talk is going to be on these photonic architectures, which really leverage non-volatile optical materials for in-memory computing, analogous to the way we see in-memory computing occurring in the analog domain for electronic crossbar arrays. So kind of translating that concept to the photonic domain to increase bandwidth and speed. So the motivation, I'm sure we're all aware, is AI computing resources are consuming a lot of computing resources, and that is just growing pretty much exponentially as time goes on. So this is not for training. Training is much worse, but for inference, which is the main application for kind of these emerging analog hardware accelerators, inference is really kind of key, because once you train your network, you have to run it many times. And in fact, the way that we see charging in terms of API keys for large language models and such is dependent on how much compute resources you use, and that is directly related to the economics of running those servers in the cloud. So at this point, data processing is much greater than the amount of compute usage needed for data storage. And current digital hardware is not able to compete in terms of how many operations you get per watt. As time goes on, we're needing more and more operations per second to achieve inference, and that just means that the difference between this curve in terms of compute usage and this curve in terms of compute performance means that it just takes more and more energy to run these services. We can note that about 90% of these compute resources are devoted to matrix vector operations, and that is where optics can really shine. So if we look at computing in the optical domain, we can take the huge multi-terahertz bandwidth of fibers. We can condense that down to something that is much smaller on an integrated silicon chip, and use single mode waveguides to route light with high refractive index contrast, so that we can have tight bends and compact a lot of what we could normally do with fiber networks onto a chip. Coupled with the fact that we have wave propagation, we can make use of ultra low energy linear transformations. This is an example in free space, but you can do the same thing on chip, where you project an image through a lens, and the lens performs a Fourier transform. You can do some sort of masking, which is a form of computing or convolution in the Fourier plane, and then another lens does the inverse Fourier transform, and then you measure the output. So in a single shot, as the light propagates from basically the left side of this image to the right side of this image, it's going through multiple linear transformations, and we are achieving, basically, as long as these are lossless media, it's just the amount of energy it takes to generate the light and detect it. So we can have high throughput, high speed, and low energy consumption if we design our systems right. So there have been a lot of works that have come out recently on optical computing for AI. It all really focuses on matrix vector multiplications. And what we have here is an example of a integrated photonic network on chip. So we're taking 4 inputs. Here we're putting it through a bunch of unitary transformations, and we're getting basically the result of an input vector times a matrix coming out here. So this is a coherent approach. We can also do diffractive neural networks, which are typically also coherent. So we shine light through these masks, and as light propagates through each mask, you encounter phase delays and scattering, which, if you tune your masks correctly, can focus these input images to a specific detector, and so that can do some sort of classification and free space imaging. And then there's a field of neuromorphic photonics, which make use of nonlinearities, usually electro-optic nonlinearities, where as you send either optical pulses or electrical pulses to some sort of laser, you can get spiking behavior. And then you can do accumulation, so weighted addition using tunable microring resonator banks. And if you use wavelength division multiplexing, you can fan this out to multiple schemes, and basically have neurons that can integrate fire and do some sort of RF processing. This can also just be interpreted as a matrix vector multiplication too, where you've got an input vector of optical wavelengths that are multiplied by these rows. So each of these basically microwave resonator banks would be the equivalent of a dot product. So there are a lot of different platforms you can play with to achieve computing in the optical domain. You have a lot of advantages where you have low energy linear transformations, low loss interconnects. You have very high bandwidth, so you can make use of a lot of different wavelengths at the same time in the same single mode waveguide. But there are significant challenges to making this really viable. So scalability is a huge challenge. For example, this is a pretty large circuit that's implementing just a 4x4 matrix, for example, up here. And there's a limited number of rings that you can have on a single bus waveguide before they start to have interference and crosstalk. So scalability is a challenge, regardless of the architecture. Tolerance to device variability is also a challenge. Directional couplers, for example, can have various yield in terms of 50-50 splitting or 49-51% splitting. That all needs to be kind of calibrated and tuned. Rings are never, when you create a micro resonator ring, you never get the exact same frequency response in each ring, even though you design it exactly the same. So this is an analog system, and similar to analog electronics, you get device variability. And then, of course, power consumption. You have to modulate these signals. You can convert between the electrical and optical domain. And you also have to convert from the analog to the digital domain, and all of that costs energy. And depending on how fast you do it, it costs more or less energy. So these are challenges that my group is looking into, and many other groups as well. So our particular flavor is that we are looking at non-volatile materials combined with integrated photonics to achieve fast, efficient, and massively parallel computing. So we can make use of the high bandwidth optical interconnects and the non-volatile materials used typically in electronic crossbar arrays and do something that is hopefully useful and interesting in terms of AI computing. So the materials that we're using are phase change materials. GST is kind of one of the most common ones. And it was used for a while in rewritable CDs. So you shine a laser and you can change bits of information by actually annealing the material, switching it between its crystalline and amorphous state. So in order to achieve this, you heat it up and it will, the atoms will organize themselves into the crystalline state, which is energetically more favorable. Or if you send a shorter pulse and you randomize the atoms and let it cool before it has a chance to reconfigure, it will stay in the amorphous state. And these two states have very high optical contrast. So you can see in the amorphous state, you have relatively low optical absorption, whereas in the the crystalline state, you have higher optical absorption because you're going from an amorphous material to basically a small bandgap semiconductor, switching between these two states. You also see a very large change in the real part of the refractive index, which is really quite impressive for any optical material. It's really challenging to get, change in refractive index on the order of 2, let alone 10 to the minus 2. So these materials are quite unique in that sense, and they have, a very large amount of rewrite cycles that are possible. They're also used in electrical crossbar arrays in 3D X-point or cross-point memory. Because in the amorphous state, it's basically an insulator. In the crystalline state, it's a low bandgap semiconductor. So you have strong conductance contrast between the crystalline and amorphous state. So this material has been industrially vetted, turned into products, and so it's a promising material to be using for this application as well. So the way that we use it for optics is we take a waveguide, single mode waveguide, we sputter this phase change material on top, and when we crystallize it, we have low optical transmission because we have high absorption. So light is absorbed along the propagation length of this material, even though we only have a few 10 nanometers or so of this phase change material, we can absorb it along the length of the waveguide and get quite strong, I think about 5 microns, you can get, close to 9 dB optical contrast between the amorphous and crystalline state. And that can change, of course, as you change the thickness of this material in the waveguide or the length. So in the amorphous state, it's mostly transparent with a little bit of loss, and you can have a mixture of this material because we're not switching the entire material between its amorphous and crystalline state. We can change domains or areas within the phase change material itself. So let's say that half of this on this side was amorphous and the other half was crystalline. You get a level somewhere in between. Fully absorptive and fully crystalline, and you can store multiple levels. And I think that the record so far is about 7 bits of precision, or 7 bits of level, so 2 to the 7 number of levels in a single phase change material memory cell, which is starting to be actually useful in terms of computation. The fact that this can be used for both for both optical and electrical memory allows you to do some kind of interesting things. So this isn't just an example of a memory cell that we made that was extremely compact, where we have a microheater on one side to switch the state of the material, but we can also measure the conductance across these two contacts. So you can see on one side, we can apply a current and heat up the material and switch it between its amorphous and crystalline state. But we can also measure the conductivity between, these two contacts and this ground contact, for example, and measure both the electrical response and the optical response as we switch this material, either in the optical, switching using optical pulses or switching using electrical pulses. And we can also see, multi-level memory in this case. And you get basically an enhancement in the interaction with this material, because we shape these electrodes in the shape of a plasmonic waveguide. So we're coupling light into a very small region. And that actually allows us to switch a small volume of this material, so we're sensitive both electrically and optically in the same volume. So this is just kind of an example of yet another way of using this material to convert information between the electrical and optical domain and vice versa. Okay, so now that we have, memory cells, and that was, just one example of many in the literature that people have been working with to switch these materials back and forth electrically and optically and use them as memory cells. But now that we actually have these memory cells, we want to put them in a neural network. And so if we look at a neural network, we've got an input vector that we can multiply by a connectivity matrix. And this connectivity matrix can be encoded in some sort of two-dimensional array of these memory cells. So if we were able to map this neural network onto a memory array, we could think of actually implementing a fully connected feed-forward neural network where information passes from the left to the right without needing to load information basically into these memory cells. And hopefully we could get a multi-layer memory or a multi-layer optical neural network in a single shot where everything could hopefully pass through in the analog domain from the left to the right and save energy and speed and increase bandwidth and so on and so forth. So that's kind of the goal, long-term goal. But in order to do that, we need to make these arrays that have multiply accumulate cells. So how do we actually achieve multiply accumulate operations where this input vector is accumulated, so multiplied by the value of each of these memory cells and accumulated along these columns. So the way that we do this is we go back to our memory cell. This is an example of using all optical multiplication, but you can also send electrical pulses and switch the state of these materials to encode information. So if we send a pulse where we change the state of this memory cell, so we're changing the transmission. If we set the transmission proportional to this value A, and then send another pulse which doesn't switch the material. This is just basically a read pulse that's proportional to the number B. We have C, which is A times B, or the transmission times this input power. And so once you set this, set the state of this memory cell, you can change B very rapidly. You can modulate the amplitude of B and measure the output power, and you're just limited basically by the modulation frequency at the input and the detection frequency at the output. To achieve accumulation, we can put two non-volatile memory cells on a waveguide and then combine them into a single output waveguide where we have two input powers multiplied by two transmission values, and that is an example of a very simple two-element dot product between two vectors. So in order to make this actually useful, we need to map to two dimensions. Instead of one dimension, we want to do matrix vector multiplication. So a nice example of where this could be useful is in edge detection. So these are examples of 4 different edge detection kernels where you're measuring transitions from left to right or right to left, top, bottom up, and trying to detect changes in pixel intensities. So we can map this to a 4x4 photonic matrix where each of these kernels are in one of the columns. And now if we scan over an image and we send in 4 input pixels at a time where the grayscale values are proportional to, optical powers between, scaled between 0 and 1, and the transmission of these memory cells are proportional, between, again, transmission between 0 and 1. We detect the optical power. We can sum up along these columns. We can use directional couplers to fan out and also fan in or accumulate. And we get results that are quite similar to what we would calculate. So once we encode this matrix, it's fixed in these memory cells. So this would be a 4x4, 16 different memory cells that are programmed. And as we sweep over the pixels, we can get an output pixel in each of these output images or feature maps in every single optical clock cycle. And the key is that if we can scan over this image very quickly and detect it very quickly, we can get these much faster than we could do it digitally. So we're achieving a full matrix vector multiplication in a single optical clock cycle. But we can do even better than that because in the optical domain, we can make use of multiple wavelengths at the same time. So let's say that we have two input vectors. So we're sending 4 pixels from each of these 2 images simultaneously. If we encode these on 2 different wavelength bands, and then do some filtering at the output, we can actually double the computational power in the same footprint. So the memory cells are still the same, the kernel values are still the same. We're just feeding in more images or more input vectors at the same time. And then this actually gives us the ability to do matrix multiplication rather than matrix vector multiplication, because now we're scaling in frequency dimension, not just spatial dimension. The nice thing about this is that you're not adding any hardware in the actual computing core. You do have to add filters and modulators, but then this is a way of having some sort of flexible scaling. So maybe you have more data that you need to process at a given time instead of investing in a bunch more software, buying or hardware, and buying more GPUs. You could think about scaling in frequency space rather than scaling in physical space, which is one of the motivations. So one of the ways that we demonstrated this was with a frequency comb from Tobias Kippenberg's group. And that was nicely spaced. That was aligned well with fiber-based multiplexers and demultiplexers. We modulated each of these inputs. So in this case, we're doing a 4x4 matrix multiplied by a 4x4 matrix, or 4 input vectors at the same time. And basically, these are the experimental results. So you can get through these images 4 times faster if you send in 4 input vectors at the same time. And then when you take the difference between these 4 edge detection or add these edge detection filters together, or sorry, output features together, you get the highlighted edges of the 2 input images. So the fact that this is a passive photonic array, we're not limited by the quality factor of any microring resonators or resonant elements, which is good. So you can you can input multiple wavelengths from a range of different wavelengths without suffering from limited bandwidth, and modulate it very quickly. We showed up to about 5 bits of precision per dot product. So this was, I think, an example of a 9 input vectors, or 9 input elements multiplied by 9 memory cells. And so it was a 9x1 dot product. So good precision for a first experimental demonstration. And if we were to scale this up, just in terms of how much operations you get per millimeter squared, optics can be very competitive if you are able to modulate it quickly. And also, this would linearly scale with how many frequency or how many wavelength bands that you can pass through the system as well. Okay, so in future work, we're quite interested in taking this initial concept, and instead of having all of these memory cells be switched optically, you could see that there's no really way to switch these memory cells electrically, because there were no electrical contacts or anything. We're interested in integrating electrical microheaters so that we can actually switch the state of the material, and integrating CMOS logic along with it so that we can have high-speed modulators, an array of memory cells on chip that we can program individually, and high-speed photodetectors so that we can take something that was taking up a whole optical table and putting it onto a single chip. And the size of this, relatively simple demonstration chip here is only a few millimeters square. Okay, so I motivated all that with high-speed computing, and it's useful for maybe the first one or two layers of a neural network where the number of trained weights is really quite small if you're doing convolutions on the first layer or two. But as you get deeper into the network and you start having fully connected layers, this becomes a significant challenge for any sort of weight stationary photonic processor. So if you have you're limited basically by the number of memory cells that you can even fit on a chip. And with billions of parameters for a neural network, how are you ever going to fit billions of memory cells on a photonic chip in a reasonable amount of space? It's just not feasible. So what this requires is that if the matrix that you're multiplying by is larger than the physical matrix that you have on chip, you're going to need to reprogram all of these memory cells multiple times. And so if we were to try to do this, with spatial parallelism, and each of these, memory cell are, each of these memory cells were 25 by 25 microns, which is pretty competitive for photonics. It would take a huge chip just to implement, 10 million memory cells on a single chip. So this is, getting close to the size of many, many reticles, let alone a full wafer. If you reprogram the array, so let's say that you're able to make a 64 by 64 array, so much smaller than 10 million memory cells, but then you needed to update the memory array many, many times in order to sweep over the entire, all the parameters that you've trained. You have significant amount of latency. You have a significant amount of energy that is required and power that's required to actually switch these non-volatile materials back and forth. So this is not really a very feasible way of scaling to large scale neural networks. And in fact, this has been investigated in other architectures where you need a certain size array dimension and you need a certain amount of power efficiency to reprogram that entire array to even make it competitive in terms of number of inferences per watt. So this is an example from of a paper from Light Matter where they're investigating this. These curves are all for different speeds and different size arrays in the optical domain compared to these are electrical state-of-the-art hardware. So you actually need to be pretty fast and implement relatively large arrays with very high efficiency memory cells in order to make this work. So this is with MEMS-based MZIs, this simulation paper. With photonic crossbar array, it's even worse. This is how much programming to compute time in energy it takes if you were to implement these, realistic models on a 64 by 64 photonic tensor core. So you can see, 10,000 is not great in terms of energy versus how much energy it takes to actually just run information through these machines. So basically, what we're seeing is that this is dominated by programming rather than compute energy and latency. So that leads us to try to look at what memory cells are out there that can be programmed quickly, can be programmed efficiently, and don't take up a ton of area on chip. So how many memory cells can you actually pack on the chip? So there really isn't a great solution out there that is stores a large number of bits in a small area and switches at high speeds. So usually, if you have a high extinction ratio or high speed switching, it usually doesn't allow you to switch multiple times. Since we've published this review work, there's been some other papers that have come out, which is nice to see. So you see quite a compact memory cell. This is, I think, 10 micron radius, micron resonator radius. And this is using electronic memristor to actually change the state of this resonance. So you can see it's switching between the set and reset state, which is good. You can see that there's maybe 3 levels, an intermediate level, and then the off and the on state. It switches very quickly, which is great, and it switches quite efficiently. But we really need memory that is approaching 6 bits of resolution in order to actually do useful computation. So this is a step in the right direction, but not quite there yet. Okay, so kind of revisiting this crossbar array concept. So what we demonstrated was an input vector that we sum up along these columns, and we're multiplying the results at each of these bends where we put memory, non-volatile memory at each of these bends. So basically, as quickly as we input this vector and detect this output, we can get we can get the result of a matrix vector multiplication, or matrix multiplication if we scale in frequency space. Well, that would not exactly sure what happened there, but imagine this entire array there as well. And instead, we're feeding information in from left to right and bottom up. Each of these intersections, we can take the interference. So we're only suffering loss from fan out rather than also fan in. And if we time multiplex our inputs, we can, at each of these intersections, have the dot product between this input vector and this input vector, and integrate over time to get the dot product. We sacrifice speed because we have to integrate over time to accumulate the dot product rather than get it in a single shot. But it also allows us to scale, not limited by the the amount of hardware that we have on the chip, or how many unit cells we have on chip. There we go. And this is inspired by Ryan Hammerly's work and Dirk England's work on this photoelectric multiplication concept, where you can take and interfere 2 beams of light on a beam splitter, and by measuring the difference between the 2 outputs, if everything is coherent, you can get homodyne detection and extract this dot product. And this is much more beneficial because now you're not limited by the size of the weight bank, because in one dimension you are inputting the vector in time, so you can integrate over thousands of time steps, and basically only need to you're only limited by the size, so that the dimensions of one of your input vectors, right, or one of one side of your matrix, and the longer dimension can be multiplexed in time. This gives you a submatrix, so then you repeat this for each column and fill out the submatrix. But at the end, you don't need to accumulate a bunch of intermediate values and add all these submatrices together. You get the final submatrix in a single step. So you save time there. As well as, if you're integrating over a longer enough period of time, you don't need super fast readout circuitry. So you can think of using an image sensor to actually read out the state of your final matrix or submatrix here. And therefore you can really reduce the ADC power that you need to use it. It doesn't have to run at the same speed basically as your input modulators. So using this type of approach, theoretically, we can achieve much better energy efficiency per multiply accumulate compared to weight stationary architectures, where the weights are programmed and reprogrammed based on the size of the matrix. So if everything fits within the size of the matrix, so if you're only doing very small matrices, 64 by 64, then you have a benefit for in terms of latency, and somewhat in terms of energy, for doing everything in a weight stationary approach. But if you have an output stationary approach, where you're integrating over the time domain, you can really benefit in terms of latency and energy consumption compared to other digital and optical approaches. So we've been working to demonstrate this on chip. The previous results were just theoretical simulations. So in this case, we can take a 3dB beam splitter that's on chip. We can have, if we modulate the amplitude and phase from a coherent source, we can essentially perform the dot product through temporal integration, or if you divide by the number of samples that you have, it'd be temporal averaging, and you can implement both the dot product and correlation in on chip, which is kind of the goal. And so if you integrate over, enough time, so these would be an example of both positive and negatively weighted inputs, signal A and signal B. We're just showing the input amplitude, but we're also changing the phase as well. So if we have, a positive and a negative number, we would get a negative differential signal versus a positive differential signal if they're both positive or they're both negative. And if you integrate this differential signal over time, so this is the result of the homodyne detection, we get something that is proportional to the dot product. And we can see that as we integrate over time, we get something that is quite good within about 3% of the actual theoretical result that we would expect. The benefit of using a coherent light source is that you have access to both positive and negative numbers, but not only that, you also have access to this imaginary plane. So if you change the phase and the amplitude arbitrarily, you can basically double the number or square basically the number of bits for the same signal to noise ratio because you have access to the imaginary plane. So here we show multiplication of two complex numbers where we have the real product and the imaginary product, so we can extract what the magnitude and the phase is based on the real and imaginary components of these multiplications, where we're changing the amplitude and we're also changing the phase of the input that's coming and interfering on the signal. We can also take this and scale this to 2 dimensions again. So that was just for, for a single unit cell that I was showing, but we can put this within a crossbar array and we can use these directional couplers for fan out. And basically at each of these input values, we can have different input vectors that are intersecting and interfering at each of these unit cells. And so the result of this would be, a 4x4 matrix output where we've got a 4 by n and an n by 4, two 4 by n and n by 4 matrices that we're multiplying together and integrating over time. So this is an example of matrix-matrix multiplication, which is coherent. And so you have access to both positive and negative numbers. And if you change the configuration here, so that you have a 90-degree hybrid, you could even have access to imaginary plane as well. So it's quite, challenging to detect, basically, 16 by 6, I guess this would be 32 different output grading couplers at the same time. So this is where an image sensor comes in, which is nice. So we have a near IR image sensor where we can take the output of these two two grading couplers for each of these unit cells, and we can compare the relative intensities. So in this case, we have either the positive grading coupler or the negative grading coupler. If we take the difference of these two intensities, we can extract what the actual value should be. So after some, clustering or binning of the optical intensities from these two grading couplers in each unit cell, we can extract what the positive output and the negative output should be. Taking the difference would give us the actual matrix. So this is an example of just sweeping the wavelength, for example. So that's changing the optical path length and changing the interference conditions. And you can see that different grading couplers light up based on the relative phase and intensity of the two of the light that's coming in from basically this column and this row. Okay, so now kind of turning more toward simulation results. So I introduced this talk by indicating that there's a lot of different approaches out there. We're not the only ones working in this field, but the goal for all of these approaches is to make something that's useful, right? You want to make something that is scalable, that you can eventually consider making, a server array of optical processors or something like that would be able to handle useful machine learning models. However, there's a lot of physics that's related to each of these different approaches that is different. Do you need to, include electro-optical conversions that are, nonlinear? You have wave propagation. You have, interaction with different materials and all of this interference throughout, a MZI mesh. So you could simulate this entire circuit, using something like numerical, where you've got all the analog and physics related effects, so that you can include noise and such like that. But that is very computationally intense, and you can't simulate anything approaching a large scale system with that. If you do a digital framework, it's going to ignore limited precision and noise that you would accumulate as you would expect from analog hardware. So we've kind of introduced an approach that's built off of PyTorch, which is analog VNN, where we can kind of abstract out all of the limited precision, normalization, attenuation, and noise, but still simulated on a digital framework with very low increased computational burden. So it's about, I think, about 10% or less to simulate an abstracted optical layer versus a fully digital layer with this framework. So for example, you've got a laser that has a certain amount of relative intensity noise, shot noise. You've got an optical modulator, which would have some jitter, have thermal noise from the driver, quantization noise from the digital analog converter, and vice versa on the output. And then you've got your weights, which have reduced precision. They also have noise, have normalization because you can't have a transmission greater than 1, for example. So this framework allows you to just drop in layers and model all of this with the PyTorch framework, and then you have access to the latest updates with PyTorch and optimizers and all that built into the PyTorch framework. So by using this framework, we can actually do relatively complicated. Well, this is a relatively simple one, but we've done even large language models now using this framework. And we can change, for example, the precision, the amount of error, the activation, and include all of that in our modeling and see what performs well under realistic optical situation. So for example, if you have 6 bits of precision, and you have, in this case, error probability is linearly proportional to the noise, we can see that certain activations perform better, and we can see that you need to have more precision in your weights versus your optical inputs, which is helpful to know. So if you have non-volatile memory, for example, you can do all of that with a relatively low precision optical inputs. We were kind of curious what was happening in the case of CLU and GLU. Why did these perform much better than these other activation classes at high errors? And so investigating this, we attribute it to the discontinuity in the derivative. So if you see ReLU has a discontinuity because it's simply a max function, whereas GLU and CLU are continuous about 0. And as we interpolate between ReLU and, in this case, GLU, we get much higher precision because, if you have jitter or, some sort of noise that is offsetting, the value, say it's negative in below 0 in some cases and above 0 in other cases, the gradient that you actually apply to the weight updates is quite different. So it's much more difficult for the machine learning model to learn with a ReLU function versus a GLU activation function. And this can just be seen in this gradient error during training. So around 0, we get a very high error for GLU, and for ReLU, and for GLU, it's much lower and much more uniform. So it kind of just averages out. You can see that the scale is very different for these two as well. And this actually plays out when you try to train models with any sort of noise. So this, again, higher error probability is higher amounts of noise. And so you can see for 6 convolutional layers, that smaller network that I showed earlier, if you have an interpolation factor or if you have ReLU or some sort of discontinuity, as you increase the error probability, the discontinuity, the effect of the discontinuity becomes more pronounced. So GLU is able to train, whereas ReLU at some of these higher error probabilities is not able to train at all. And as you get to a more complicated, for example, VGG model, where you have 11 convolutional layers, the results are much more pronounced. So GLU is able to handle some amount of error, up to about 0.4 or 40% error probability, whereas ReLU is not able to train really at any of these values. This is all for the Cypher 10 data set. And I think that this is a good sign for optics and analog neural networks in general, where it's quite difficult to implement a perfect ReLU function in the analog domain, and it's much better to try to do something that is fully analog and therefore would be continuous. And our results seem to indicate that it doesn't really matter. Well, our results seem to indicate that you shouldn't be trying to replicate ReLU precisely. That having a continuous function that is continuous at 0 is actually good for training and being able to have the model learn appropriately. Okay, so with that, I'd like to thank the students that worked on these projects and the funding sources and collaborators that we've had over the course of several years. And I'd be happy to answer any questions that you would have.
Okay. Thanks, Professor Youngblood, for giving us the great talk. And now we are going to the Q&A session. So if anyone in the audience have a question, now is the time to unmute yourself and ask the question. I will pause for a few seconds.
Can we ask a question? Can you hear me?
Yes, yes.
Hello, Professor Nathan. Thanks for the talk. This is really a great talk. I had one question regarding the coherent systems for these optical computing. So I have seen that there is if you have long fibers in the benchtop components in the setup, they sometimes cause phase fluctuations. So in this case, how do you control the phases of the inputs going into these arrays in the measurement setup? I guess it also depends on the time scale that you're looking at. So if you have a time scale lesser than a microsecond or so, it might be okay. But yeah, higher than that, I think we see phase fluctuations, right? Like, how do you handle that in the measurements?
Yeah, that's an excellent question. And the answer to that is you want to have a laser source that is fiber coupled to your input and then fan that out to every single modulator. So everything is on chip. And as long as you can, control the temperature on chip pretty uniformly, you don't have to worry about that basically, because the entire thing is basically on a heat sink, and it's all referenced to the same input waveguide.
I see. So basically, you're saying that since everything is on chip, it is precisely controlled, rather than like having all the inputs directly go into the on chip on the mesh. Okay, we have split on chip. I see.
With fibers, that's the kind of the key thing is you have mechanical vibrations, you have thermal fluctuations that are not uniform over the entire length of the fiber, and that's where you get accumulated path length differences.
Got it. Thank you.
I think I see a hand raised.
Yes. So I want to ask if the bit precision result that you presented for the photonic crispr is just for the multiplication, or both the multiplication and the accumulation?
For the complex? Is that what you're asking?
No, for the tensor core, for the Nature paper.
Oh, so are you talking about for this array or for the incoherent one?
I mean the Nature paper in 2021 presented.
Okay, so this one?
Yes.
Yep.
Yeah, the bit precision you presented it's just for the multiplication of both multiplication and accumulation.
That's multiplication and accumulation. So we made a 9x4, I think, array. So we had 9 optical inputs, and you know, each goes to one column, right? So in this case, you program and set the weights, and those are fixed, and then you modulate the optical input. So this is really kind of measuring the precision of the optical input once you've accurately set the weights of your memory array.
And for the complex multiplication, it's also the multiplication of both multiplication and accumulation.
This is only for multiplication.
Okay.
So yeah, for this, we actually had to, since we didn't have a 90-degree hybrid, we had to perform the multiplication in 2 steps. So we have access, yeah, so we have access to phase control here. So we can get the 2 quadratures, so we can do the sine and the cosine by just changing this by pi over 2, I believe. And in that sense, we can measure the real product first, and then we do the same measurement again to get the imaginary product, if that makes sense.
Okay.
So these are 2 separate, measurements.
Okay. So for the bit precision of the multiplication and accumulation, if you suppose you increase the size of this process, for example, you accumulate more vector products, what will the bit precision changes?
That is a good question. So it depends, you know, it kind of depends on the distribution of the inputs. So if the result, you know, basically, if I go back here, if the final result is something that is very close to 0, you're going to suffer because the precision, like you accumulate, I mean, it's basically, you know, the accumulation of a bunch of errors, right, as you go along the length of your integration time, right? So it might be pretty precise at the beginning, but as you start to accumulate errors, you start to get farther and farther away from the ideal line, and that leads to errors as you go along. So if the final result is close to 0, and then your errors are larger than, you know, the precision that you expect at the output, then that can become a problem. This is something that we haven't really looked into very carefully. We've just assumed that we're limited by, you know, the resolution of the shot noise, or the noise from shot noise, both photonic and electronic in terms of the theory. But in terms of practice, you're never going to be able to precisely set the, you know, the amplitude and phase exactly, and there's going to be some sort of error that accumulates along, and that's going to be, I think that ends up being a random walk, and so I think it's proportional to the square root of n, or where the square root, or where n is the number of your samples.
Okay, thank you.
Okay. So then,
can I also
any other questions?
Yeah, can I also ask a question? Yeah. So can you go back to that bit precision plot?
This one, or the
this one, yeah. I noticed that, for example, in that red distribution, there isn't any value close to 0 or close to 1. Is this an artifact of like how you sample the random vectors?
Yeah, that's a good question. So because this is accumulating 9 elements, and all these 9 elements are just randomly generated, it's very unlikely that all 9 are going to be 0.
Okay. So you are just coming from a uniform distribution so that your product is like distributed like this, right?
Yeah.
So I'm wondering, like, if there's a better way, like we can sample the system so that the product will be like uniform from 0 to 1, or is this a standard way to benchmark this dot product?
That's a good question. Everyone kind of does it differently. So you know, you could manually set it so that you have a sampling from each of the, you know, possible values. yeah, that's not the way that that we did it in this case. But
Okay, I see. And for another point that you made, like the difference between a discontinuous derivative of that activation, can you go to that slide? Yeah, so is that accuracy you measured in experiment or in simulation?
this is all simulation with this analog BNN framework.
Okay, I see. Have you done any like kind of experiment with your matrix multiplication device in experiment with machine learning tasks?
We haven't. And
Okay.
the thing is, you need to, for this to become, a significant problem, you need to do something more complicated than MNIST. You need to actually be doing some useful machine learning, and you could argue that Cipher 10 is not useful at all. But at least it, the error propagates more significantly as the number of layers increases and such. So what we're saying here is that if you use a digital ReLU, for example, but you are limited by the precision of your inputs. Let's say you've got discretized inputs, it's not continuous. As you have error from noise through your system, sometimes a value close to 0 is going to have a derivative of 0, and sometimes it's going to have a derivative of 1. It's going to be very discontinuous. And as it's trying to train, those values of weights are going to keep on jumping and having large updates when you're doing propagation. Whereas if you have a continuous function about 0, that is not a really much of a
yeah. But I remember in one of your research, you mentioned like you are using to modulate the intensity. Right? In that case, your intensity is like continuous instead of discrete, right?
Your intensity is, but there's always noise, right? So when, for example, your summation is close to 0, so this would be like the output of one of your activation functions, right? Or one of your activation, like, you sum it all up, and if you have positive and negative values and you're close to 0, you have that fluctuation around 0, and sometimes it's going to be positive, sometimes it's going to be negative. And if you have a discontinuity at 0 in terms of the derivative, you're going to jump between the two.
I see.
And that makes training very difficult.
Okay, I see. And you mentioned like those CFR 10, for example, network is too deep so that you cannot do it in experiment. I wonder why, because if you modulate with a then like the bandwidth of the can be like gigahertz, right? But in that case, I think you should probably be able to simulate very deep neural networks, right? Experimentally.
Yeah. Yes, but it kind of comes down to the situation where, I mean, the largest we've done is a 9x4 array, and there are 1.7 million parameters in that relatively small model for Cipher 10. So you would have to update. You could either choose to implement this, and you'd still have to update it multiple times as you send information through it.
Yeah.
But like trying to do all of these layers, like, you have about 500,000 parameters just in, these connectors here.
I see. But in your another work, like when you modulate the amplitude with and do a homodyne detection,
yes,
in that experiment, you are not limited by this, and you are limited by like maybe the bandwidth of the but the can have a very high bandwidth, right?
Right, exactly. So that's what motivates, maybe this first few layers of convolutional layers you could actually implement on chip, because it's relatively, small number of kernel values, whereas once you get deeper and deeper into the network, the parameters start to blow up, and you'd need to do some sort of time multiplexed approach.
So do you think you can do a very deep neural network with that homodyne detection experiment?
Yeah, and in fact, Dirk England's group actually, I think, have done a couple of examples. So there's the Netcast paper, which is a really nice work where it's an incoherent time multiplexed approach. And then they also did a coherent free space approach with VXLs. And I think that they simulated, experimentally an entire neural network. Again, it was, I think, MNIST. So whether or not that's particularly interesting is another question, but it at least is capable of doing what you're saying.
Okay, I see. Thank you.
Yep.
Okay. Yeah, so actually I have another question related to what just being asked. So Professor, I know there are a lot of experimental results on demonstrating photonic neural network on MNIST, but there are only few limited works on demonstrating experiments larger than MNIST, say CVAR10 you consider here. But I wonder, so my personal feeling is the most important thing to prevent the scalability of this kind of real experiment work is because of the error accumulation. So actually we have a larger, deeper neural network with a lot of layers. And so as you just show, like a 9x4 array has like 6-bit accuracy precision of the MAC operation. But when we have a deeper neural network, probably the error will accumulate. So we cannot have a very useful and working demonstration. So this is my confusion. And what will you comment on, like the ultimate scalability of this photonic neural network in the future?
Yeah, so that's really what motivated us to do this work with analog VNN. So I would encourage you to look at that. So kind of the main conclusion is, for MNIST, you can train a rock to recognize MNIST. But with anything more complicated in terms of, Cipher10 or ImageNet or anything like that, you can actually do quite a bit with 4 to 6 bits of precision in your weights. So the weights matter more than the inputs. And it is possible, like even with a certain amount of error. So we kind of define this error probability to be, what is the probability that, if you had a digital value that was, you've reduced everything down to 6 bits of precision. And now what is the probability that that value is exactly that digital value that you are representing in this reduced precision form? So 80% would mean that only 20% of the time you're sending the actual correct value, 80% of the time you're sending a value that's, somewhere outside of that range or not that. And you can, you do suffer accuracy, but, through some of these things that I've discussed, you can make a neural network that does function pretty close to, the right accuracy, or, the maximum accuracy with, as in digital or 0 error. If you have, high enough resolution weights, and that is usually like 4 to 6 bits in that range. Anything below that, it starts to not be able to be trained.
Okay. Yeah, I see another person raising their hand. But before asking the question, I just want to double check with Professor. So because we are already going a little bit long in the time, so how long can you stay here?
Oh, me?
Yeah,
I'm
right.
I'm happy. I don't have anything right now, so I'm happy to.
Okay, cool. Then we will go on. So I see another person raised the hand, so you can ask your question.
Yeah, hello again, Professor Nathan. I just have one quick comment actually. So to quickly introduce myself, I'm Prerna. I'm currently working with HPE Labs on optical computing systems, where we are seeing some issues with the measurement setups when we calibrate the phases from these systems. So I think here is where we could use your expertise to solve some of the issues that we're seeing. So I thought it'd be great if we could connect offline. I'll take a closer look at your prior work and reach out to you if that sounds okay.
Sure. Yeah.
Okay, thank you. And also, I think it'll be great to have this recording for the talk for future reference, if that's okay. So that's the request to the host and you as well.
Yep.
Yep. Thank you. That's all right. Thanks.
Okay. Then we will go through some questions in the chat room. So the first question is from Daniel. When we use multiple wavelength channels, photonic computing inevitably is impacted by, I guess, wavelength dispersion. So I wonder how much error will be introduced, and how we mitigate this problem.
Yeah, that's a good question. So for example, here, right? You have to have different wavelengths so that you don't get interference and beating and stuff like that as you send light through these waveguides. The main limitation is these directional couplers. So first of all, the directional couplers need to be relatively broadband, and that gets worse the closer to 50% coupling you get, right? Just from the, it's proportional to the sine or cosine coupling equation. So that's one issue. There's work to make that broadband. The main thing that you need to do is make sure that the separation between these wavelengths is in frequency space larger than the bandwidth that you're detecting over. So let's say that these, this is, a certain wavelength, and this is separated by 20 gigahertz, and this is another 20 gigahertz over in this spectral band. And in this case, we had a separation of 100 gigahertz, which was well outside of our bandwidth of our photodetectors. But if the photodetectors are detecting, if this is 10 gigahertz separation and the photodetectors are detecting at 40 gigahertz, you're going to get beating between, these neighboring wavelengths. So then that makes you require a larger window, right, if you want to fit in a larger number of inputs or vectors. And then, of course, yeah, dispersion starts to play a role in terms of timing. But I think primarily in the wavelength range that we're talking about, it's limited by those directional couplers. So that's kind of the first thing that would be a limitation. What would be interesting and hasn't really been explored that much is if you take a source that is not a great coherent source, right? So let's say that you have an input source that is broadband, for example, a superluminescent LED or spontaneous ASE source, and you filter with a bandwidth that's, let's say that you have these bands, but they're 100 gigahertz in width, spectral width. And then you send those through the network, you could, you would reduce the effects of beating in that case if you had some delays between the different lines, if they weren't, if the path length was not exactly matched. And in that case, you might be able to do a lot more within, the same wavelength range, and you wouldn't have to worry about the interference. But then you suffer from relative intensity noise of those incoherent sources and stuff like that. So it's all kind of a trade-off, and it'd be interesting to look more into the incoherent light sources.
Okay, so the second question is from Yue Chen. Crossbar some partial products using combiners, which will have cascaded loss. Is it better to use MR switches to combine them to the same bus? Is the scalability of the array constrained by comp laser power?
Yeah, that's also a great question. So when you're designing the system, it's important to determine, is the majority of my loss due to electro-optical conversion? Is it, or in terms of energy efficiency, is it dominated by the digital signal processing at the output? If the optical power is a very small fraction of the total power budget of your system, then it's not as big a deal if you have these combined losses, if that kind of makes sense. If these become, start to become a big issue, then yes, you could use, for example, microring resonators or Bragg gratings, for example, directional couplers with Bragg gratings, which would now include some sort of spectral response, which would limit your bandwidth. And then for the same reasons that we talked about earlier, that would basically limit how much computing throughput you could have. So these are all trade-offs that you have to take into account. The nice thing about the broadcast and weight with those microring resonators or the coherent approach is that you don't have those recombination losses. But you're always going to have fan-out loss. So this fan-out loss is inevitable regardless of your architecture. But the fan-in loss, if you do an incoherent approach, you're always going to have that recombination loss that you mentioned.
Okay. The next question is from Jinchen Zhao. Have you tried any standard machine learning task with your device?
No. I mean, MNIST, I think the first layer of MNIST was implemented with this, where you just take the edge detection and then you put the rest of the layers through a digital processor. I think that's pretty typical in the literature, where it is quite difficult to actually implement a full-scale neural network.
Yes. Okay. Next question is from Jiaqi. MEMS-based MZI PCMX bar are with stationary tensor cores. How the attention in BERT is mapped. The dynamic attention might require frequent reprogramming of the crossbar, which can hardly amortize the weight programming cost.
Yes, that is a great question. You can see that for BERT, the throughput definitely goes down. And I don't know if that's how related. I think it does have to do with how much reuse you can get when you set the weights, how much reuse you can get as you batch the inputs. So I'm not exactly sure if they talk too much about that in the details of this work, but ResNet, which is more convolutional based as opposed to BERT, obviously performs better because of reuse.
And the next question from Huang Li. For the coherent photonic arrays, different optical path has different length, and it requires strict phase control. How the phases got calibrated for the n-square path pairs the crossbar?
Yes, that's a great question. And that is why we haven't fully demonstrated computation on this system yet. However, you can, if you design the system right, you can path match length these inputs. So for example, if what you want is A4 and B1 at this point to be path match length, or path length matched, sorry. So if the distance from here all the way to this point and from here all the way to this point is matched, then you're good. So you can play some geometrical, you can play with geometry of these input waveguides to fix that, so that you're close to approaching the right value. And then you can do some trimming within each unit cell to precisely match the path length and get the pi/2 relationship so that you maximize the contrast between these two. And you can see as we change the wavelength, some of these are fully interfering in one side, whereas the others are fully interfering on the other side or close to it. And that would be indicating the relative phase between the two at different wavelengths.
And yeah, okay. I think the final question, how is the scalability of photonic crossbar array against the electronic GPUs, AI processors in terms of multiply accumulate operations per joule with increasing matrix size?
Yes. So we have a theoretical paper on that. This is not including so it's a bit of an unfair comparison, to be completely honest. I'm not an architecture guy, so I can't really simulate, what does it cost to fetch from memory and do all of this. But if you take into account the input modulators, the optical power, the digital to analog converters, EO conversions, all of that, the photodetector current that you need to get relative, noise. The best you can do is what's plotted here for these different architectures. And for this MZI, I think the only one that had been demonstrated at this point was the that had been published anyway, was the thermal-based MZI structures, not even at a 64x64 scale. So this is based on thermal MZIs, not necessarily the MEMS-based MZIs, which we don't have any metrics for because that hasn't really been published.
Okay. Yeah. So I think that's all for the Q&A session, and it's really great to have Professor Youngblood here, and thanks for the time to stay here and answer all the questions. And I think that's the end of our today's seminar. And if you have more questions, please feel free to reach out to Professor Youngblood offline. And slides and videos will be online after confirming with Professor Youngblood. And thanks for everyone joining the seminar, and especially thanks Professor for the talk. And then welcome to subscribe our mail list and follow our future seminar events. Then I guess that's it for today.
Thanks. It was great.
Yeah, thanks, Nathan.
Bye.